Swayam Prabha. Digital India. Educated India.
Hello, welcome to lecture 13, first part. In this lecture, we'll be covering a 4-port device, which are also called couplers. Now, couplers are assumed to be lossless, reciprocal, and also, as we shall see, they can be matched at all ports. So, in the previous lecture, we had covered the 1, 2, and 3-port devices. Throughout this lecture, we'll be covering the various aspects of coupler design. So for this first part, we'll be concentrating on the mathematics behind the couplers. So just like we had done for 1-port, 2-port, and 3-port devices, we shall here be concentrating on what the S parameters should be if the system is lossless, reciprocal, and matched at all. So let me share my screen. So a coupler is a 4-port device. So by 4-port device means we can draw the symbol of a coupler like this. This is the symbol of a coupler. The numbering has a significance when we talk about coupler. This is called the coupled port. This is called the through port. This is the input port, and this is the isolated port. So since it's a 4-port device, the S parameter matrix should be a 4x4 matrix, right? So let me write all the S parameters, and then we shall see what should be the properties of the various parameters. So first of all, ports, so the properties of the S parameter. First is that port 1 and 2 and ports 3 and 4 are isolated. So this is port 3 and 4, and this is port 1 and 2. So they are isolated. Okay. So if they are isolated, then what does it mean? That it means S21 is equal to S12 is equal to 0, and S34 equal to S43 equal to 0. Okay. And then second property is ports 3 and 4 are coupled to port 1. Okay, so this implies S31 not equal to 0, S41 not equal to 0, S13 not equal to 0, and S14 not equal to 0, right? Okay, so the next property is that ports 1 and 2 are coupled to port 3. So this again means that S31 not equal to 0, S32 not equal to 0, S13 not equal to 0, and S23 not equal to 0. Okay. So next property is that uh, ports 2 and 3 are matched. Then this implies S22 equal to S33 equal to 0, and if property is the the device is reciprocal. So this implies Sij equal to Sji. Okay. So now, with that in mind, let us try to derive the other property. So assuming that the device is lossless, the, the unitary condition should be valid. Okay. Now, if I incorporate these properties that we have just derived, then what do we get? First of all, due to reciprocity, we can change these values like this. Okay, because ports 2 and 3 are matched, so we can simply replace these two with 0. So also because port 1 and 2 are isolated, so these will become 0. Same is the case with ports 3 and 4. So then we can from here imply, right, write down the whole S parameter matrix. and this will be equal to the identity matrix. So now suppose I multiply row 1 of this matrix with column 3 of this matrix. What do I get? So row 1 means this row, column 3 this one. Then what do I get? I get S11, S31 conjugate equal to 0. Now we already know that S31 cannot be 0. This one. Hence S31 conjugate also cannot be 0. So then in order to satisfy this equation, we have to have S11 equal to 0. Similarly, if I multiply row 4 with column 1, so row 4 means this row with column 1, then that will imply uh, that will imply let me write it down, S41 S11 conjugate plus S44 S42 conjugate equal to 0. Now S4 S11, now we have seen that S11 is 0, right? And S11 conjugate should also be 0. So then the term that will be left is this one. Sorry, S44 S. So we have already seen that S41 cannot be 0 because port 1 has to be coupled to port 4. So from here then we can say that S44 is equal to 0. So what we observe is that when ports 2 and 3 are matched, ports 1 and 4 are also matched. Okay? So that means, so we can then simplify our matrix further so that now these terms are also 0. Let me write down the S parameter matrix. So what we have, from what we have gathered so far, our S parameter matrix should be like this. So this is how our S parameter matrix of a coupler should be. Right? So then if we further go ahead with this unitary condition, let me once again write this equation. Now, suppose I multiply row 1 with column 2. So this is row 1 and this is column 2. That will imply S31, S32 conjugate plus S41, S42 conjugate is equal to 0. And if I multiply row 3 into column 4, so this is row 3 multiplied by column 4, what do I get? Now from this I can write and from this also I can write might be wondering why I'm not writing the conjugate term here or here. That's because I'm taking the modulus only. S31 is equal to 41. By equating these two equations, what we get? We get so this is one equation that we get. Similarly, suppose we want to eliminate. So, for example, this equation I can rewrite it as and this equation I can rewrite it as so again equating these two equations, what we get S42 mod is equal to S31 mod. Now let me call this S31 mod equal to this equation. Let me write this as equal to AT. Now why? What does that T in the subscript signify? Let me redraw the symbol for coupler. So here the power that flows from input to the through port, that is dependent on this quantity. Similarly, the power, if suppose we are inputting at port 2, then the power that flows to the through port for 2, that is port 3, is given dependent on this quantity. Hence, T, the small t, represents the transmission. And the other relation that we got, sorry, not this one. Transmission parameter is this one, Kt. And this parameter, we will call it as Kc, because C implies coupled power. So, for example, the power that is going from input port 1 to the port coupled port 3 is dependent on this parameter. Similarly, the power that is going from input port 2 to coupled port for input port 2 4. So for if I input power at 2, then 4 is the coupled port for input port 2, and then the coupling factor S42 determines how much power is flowing from port 2 to port 4. Hence this term Kc, C representing the coupled. Okay. Now further, if I multiply port row 1 times column 1, then that implies S31 square plus mod S41 equal to 1. S31 is equal to Kc square and S41 is equal to Kt square, and the sum of the squares is equal to 1. Now, we can, just like we saw for the T's, where we can adjust the phase of the S parameter by adjusting the various port lengths. So by adjusting, say, the lengths of port 1 and 4, it is possible that we can make S41 equal to Kt with 0 phase, and also S32, note that modulus of S41 and S32 are the same. I can also make S32 purely real. So now let me define S31, which has a magnitude of Kc, but let me assign a phase theta. Okay, and let me substitute in this equation all the values that we just assigned. Let me substitute all these values in this equation. So then what do we get? From this equation, if we substitute all these values in this equation, what we get is Kc, S31 is Kc e raised to j theta, S32 conjugate is Kt, S41 is Kt, and S42 conjugate is unknown, and that is equal to 0. So from here, S42 conjugate is equal to minus Kc raised to j theta. I can also write as equal to Kc raised to j theta minus phi, and then from here S42 will be equal to like this. Now, depending on what value of theta we choose, before going to that, let me then write down the S parameter matrix in terms of Kc, Kt, and theta. S31 is equal to Ac, S41 At. This is also okay. S32 is equal to Kt, and S42 is equal to Ac J phi minus theta, like this. Now, depending on what we assign the value of theta, we can have two types of couplers. Now, why two? I will come to that later. But suppose when for theta equal to pi by 2 or 90 degree, when theta is equal to pi by 2 or 90 degree, we obtain a set of couplers which are called 90-degree couplers. And the S parameter matrix for that is okay. And for theta equal to 0, we obtain another set of couplers which are called 180-degree couplers. Okay, so 180-degree couplers, for 180-degree couplers, theta is 0, not 180 degree. And the S parameter matrix will be like this. Plus, sorry, and this is minus. Now you might wonder why we have only two types of coupler, isn't it? I mean, we could have chosen theta to be any value. The reason is the utility. For most cases, we either need a pi by 2 phase shift, for example, in a quarter wave transformer, we have to have pi by 2 phase shift, or we need a 180-degree phase shift. Other than these two phase shifts, we really don't have any other phase need of any. We don't have the need of any other phase shifts. And the second thing is, say if we had this theta equal to some other value like pi by 4, like that is 45 degree, then it's rather difficult to implement it. So theoretically we have a solution, but to actually implement that, it's quite difficult. By the way, the Butler matrix project that I have given, that is an example of when say theta equal to a multiple of pi by 4. Now, as far as couplers, for practical couplers, there are some metrics for evaluating the coupling, how good the coupler is. So some of the parameters are the coupling coefficient, C is equal to minus 10 log 10 of S31. It's a measure of uh, how good the coupling is. So if S31, for example, is very low, then C will be very high and positive. So it's like if the coupling is not good, then C is very high. If the coupling is very good, that is say S31 is nearly equal to 1, then C has a low value. Isolation, that is another parameter or a metric for evaluating the performance of a coupler. And I is given by so once again, if the isolation is very bad, for example S21 is nearly equal to 1, then I will be very low. On the other hand, if port 2 is well isolated from port 1, I will be very high. So another coefficient is known as directivity. D is given by I minus C. It's like if isolation is very good, then directivity is high. Or suppose if the coupling is very high, that is very less power is going to port 3, then directivity is also is very poor. Okay, so directivity is a measure of how much power is going to the through port. Okay, typical values for C, I, and D are C is equal to say 20 dB. It is considered good. D equal to 20 dB. It is also considered good. And I equal to 40 dB is also considered good. So with that, I come to an end to this part. In the next part of lecture 30, we'll be covering the individual couplers and seeing how to design. So in the previous part, we just covered the mathematical framework of four-port couplers. In this part, we'll actually discuss the various types of couplers. So, couplers, as I said, are of two types. We just discussed it in the previous part. So among 90-degree couplers, my screen visible? Yes. So among 90-degree couplers, we have coupled line couplers, then branch line couplers, and line couplers. Among 180-degree, we have magic T, rat race, tapered line coupler. So let me uh, we'll cover some of them, not all. So we'll be we'll be discussing about branch line couplers, coupled line couplers, magic T, and rat race couplers. So magic. Let us start first with the magic T. So magic T is an example of a 180-degree coupler. shape of the magic T is a combination of the H plane and E plane T. So suppose first I draw an H plane T. Like a combination of both an E plane T and a H plane T. So this part is the H plane T and part is the E plane T. The ports are numbered as this is port 2, this is port 3. The numbering retains the sense in the sense that if port 1 is the input port, then port 2 will be the should be the isolated port, port 3 should be the coupled port, and port 4 should be the through port. So if we consider the E plane part of this magic T, then some of the parameters are self-evident. So first of all, see in a E plane T, electric field lines are between the faces which are closest to each other. Where similarly in the H plane T also, the electric fields are between the faces which are closest to each other, and so on like this. So what happens is that uh, any signal that is inputted, say at port 1, because of this peculiar shape of the electric fields between E plane and H plane T, no signal passes from port 1 to port 2. And that's why port 1 and port 2 are isolated. So S12 will be equal to 0, and so will S21. Then we have, considering the E plane T part, S41 will be equal to minus S31, and then similarly considering the H plane T part, we'll have S42 equal to S32 1 by root 2. So, suppose we write down the S parameter matrix. So all the ports are matched. Then S12 is 0, S21 is 0. Then S41, this is 1, 3 minus. Okay. Then S32 is equal to 1 upon square root of 2. Then we have S43 sorry S4 is S42, so this is also very S43. We don't know what is S4. Let's just write it like that. And S conjugate transpose equal to 0 upon root So now, if we multiply, let's multiply row 1 with uh, with column 4. Let's write this properly. So row 1 into column 4. Okay, this will imply minus 1 upon square root of 2 into S of 4 3 conjugate equal to 0. So from here we see that S of 4 3 should also be equal to 0. So this proves that for a magic T structure, the ports 3 and 4 will also be isolated. Okay? And so then the resulting S parameter matrix will be like this. So we can remove these two. Okay? So this is the final S parameter matrix of a magic T. And it is an example of a 180-degree coupling. You see why? Because we have this negative terms here. Okay. Let us now discuss the branch line hybrid coupling. So, and by the way, the term hybrid coupler means when there is equal power division So what this means is that S31 magnitude is equal to S41 magnitude. Okay. So what is the schematic of a branch line hybrid? A branch line hybrid, first of all, I'll draw the structure, how it looks like on fabricated. And for your project, you will need this branch line hybrid. Now, for a branch line hybrid, as you can see, the port order is same as that for the symbol of a coupler. It is this is 1 followed by 2 here, this is 3, this is 4. But that is not always the case. For example, ports 1 and 2 for example, the rat race coupler, they need not be adjacent to each other. Now, this length of each of these segments is lambda by 4. So for example, this is lambda by 4. And this is lambda by 4. And so this is Z0 represents the connectors, whereas within the branch line hybrid, there are transmission lines having two different characteristic impedances. One is Z1, the other is Z2. Okay, so now this is the way it looks like, okay, on a PCB board, but the schematic can be simplified like this. So I just draw the schematic diagram. Is like this. Okay. Now let us try to analyze this mathematically. Okay. First of all, I would further simplify the schematic and draw these transmission lines by simple straight line. So what I mean is, further simplifying this one. I draw a line of symmetry like this. So once again, this length is lambda by 4. This is Z1. This is Z2. This length is lambda by 8. This length is also lambda by 8. Okay. Then this is port 3. This is port 4. Port 2. This is port 1. We make them a little thicker so that you can understand that these are actually transmission line segments. Two will be here. So now the way we will analyze this is what we call the even odd mode analysis, which is similar to what we saw for the Wilkinson power divider. So here, say if I introduce a signal A1 incident at this port, then that can be resolved like this into two modes as a combination of two modes.